Welcome to chapter 11. We're going to be talking about energy, the different forms of it, and of course, as it says, its conservation. We'll talk about what that means in time. There is a little launch lab that you can do at home pretty easily. If you want to give that a try, I think it has some good lessons to teach. In the first section of the reading, there's a lot of talk about the different forms of energy and how to transform back and forth between those. But I also want you to pay attention to that term reference level, especially to pay attention to that one. The book's going to give you a bit of an analogy here for, tracking money, accounting basically, and energy changes. It's useful to an extent, but basically we're going to be looking at bar graphs and how those bar graphs kind of add up to give you your final system amount of energy. So you can see this in the example of the ball here. At the beginning, the ball has 0 kinetic energy. Then you do a certain amount of work. And as we know, work equals the change in kinetic energy. So you're going to end up with a certain amount of kinetic energy after, right, when you throw the ball, basically. And then when the ball comes to a stop, when it's caught, that kinetic energy is going to be lost by negative work, right? You're going to do a certain amount of negative work. So notice the bar graph is below the 0 line. Okay. Anyway, so we have different kinds of energy, we said. Kinetic, you should be familiar with. Translational kinetic energy is 1/2 mv squared, right? Saying that it's proportional to the mass and it's proportional to the square of the speed, meaning that if you double the speed, like going from 10 meters per second to 20 meters per second, doubling the speed is going to quadruple the kinetic energy. They also do talk about rotational kinetic energy, but we sort of skipped that earlier, so we're not going to go into that here. Potential energy, on the other hand, is sort of a stored energy. I like to think, though, of it in terms of position, because in every case, potential energy is due to where the objects are at, right? So if you have two objects that are, with some mass and they're close together, there will be a gravitational potential energy between them. If you have like a spring and you compress that spring, right, you change the position of the sides of the spring, that's going to cause elastic potential energy. So different forms of potential energy are all due to position, really. Now, gravity does a certain amount of work on objects, right? So if you throw a ball up into the air, right, as you throw that ball up into the air, gravity is going to be acting downward even though it is moving upward, right? And so gravity is actually doing negative work, right? The force of gravity is pointing in the opposite direction of the displacement. And so therefore, we have negative work. So that's why you see Wg is equal to negative mgh. When an object is falling down, on the other hand, gravity is going to be doing positive work, right? So again, mg is now going to be pointing down. The force, well, it's always pointing down. The force is pointing down, right? And the displacement is down. And so that's going to be positive work. So that's why things speed up when they're falling down, right? And they slow down as they go upward. That kind of makes sense. Okay. Now they have a little picture here of what's going on with the energy in this. Well, this is juggling. This girl is juggling some oranges. As an orange flies into the air, it has kinetic energy when she first throws it. That gets transformed into potential energy as it gets higher, right? So the higher it gets, the more potential energy it has, until it comes to a stop, right? When it gets to the top of the flight, it no longer has kinetic energy since it's stopped, but it does have its maximum potential energy. And in fact, however much kinetic energy it started with is basically going to be how much potential energy it has at the top, okay, minus a little, air resistance and such, okay? And then it's going to fall back down, and as it falls back down, the potential energy transforms back into kinetic energy. Okay, so this is really sort of one of the keys of this this unit or this section. is this little diagram. It really helps you to understand what's going on. Now note that there is a reference level that's assumed in that picture. Okay, the reference level that's assumed is actually her hand. When it leaves her hand, it's said to have zero potential energy, right? And then it has zero potential energy when it comes back to her hand. Though you don't have to pick that as the reference level. You could have picked any point to be zero. You could have picked the ground to be zero, and that would have been valid too. You could have done the problem that way. You could have picked the top of the flight to be zero, but usually we pick whatever seems to be the most convenient, right? So start of motion, perhaps, wherever the motion starts. Anyway, once you have a reference level, you need the height, the mass, and of course G, and you put them together, and that will give you the gravitational potential energy. So that's why you see GPE is equal to mgh. Okay. As I said, you can pick any height for the reference level that's convenient. This little graphic, figure 5, sort of takes you through, what happens if you choose a different reference level. You can try that yourself. Then there's some example problems, of course, go through those. And then the book talks through a couple of other types of energy, right? Elastic potential energy, which you can see in a bow and arrow, you can see it in a pole vault, you can see it in a spring, of course. And rest energy from Einstein's famous E equals mc squared equation, other kinds of energy are, of course, out there. And the point is, though, that matter can always be converting back and forth between these different kinds of energy. So you want to check all those out and understand them. And then, of course, answer the questions at the end of the section.